Good morning, everyone. Welcome to DevOps Pro conference. And I'm Michiel Rook, and I'm excited to be hosting today's opening keynote. Before we get started, though, let me introduce a few things about this conference, about this year's conference. So because everything is digital, I can't see all of you, of course. It would be awesome if you can all share which country, which city you are from, and put that in the chat. The conference, as you can see right now, is hosted on Pine. And so let me share a few of the features in this platform with you. Take a look at the screen. You can access Pine through the web, but also through a mobile app on your phone. All of the sessions will be recorded. All of the sessions can be accessed via the virtual stages menu. Different sessions are going to be on different stages. So you're now on the Kubernetes stage, but other sessions will be on other stages today. And it might be hard to choose what to attend, which session you want to see. So take a look at all the sessions and all the speakers, and you can then bookmark the sessions that you think are interesting. Everyone is encouraged to fill in their user profile. Go to the top right corner of the Pine platform, and then you can check your messages there as well, and you can connect with other attendees by clicking on their profile and leave a message. Lastly, make sure that you visit the virtual expo. So there's a couple of sponsors that want to talk to you, that want to share what they're doing, and they're waiting for you over there. So please go ahead and visit them. And about those sponsors, let me share a few things about some of those sponsors for DevOps Pro today. So the first one is our platinum sponsor, which is Sonatype, which is a well-known company, and more than 10 million software developers worldwide rely on Sonatype to innovate faster while mitigating security risks that are inherent in open source. Okay, Sonatype's Nexus platform, you may notice, combines in-depth component intelligence with real-time remediation guidance to automate and scale open source governance across every stage of the modern DevOps pipeline. So if you use open source components, and most of us do, and you want to know if there are vulnerabilities there, go ahead and check out Sonatype Nexus. And also make sure you participate in their campaign and get a free t-shirt. Sounds pretty cool. Number two, SbearMarket, and I hope I pronounced this right. SbearMarket is a technological online service that helps you make purchases without leaving your home, and that's pretty cool. SbearMarket was created on the basis of a startup called Instamart, and it joined the Sbear ecosystem in 2019. Last year, the R&D team grew 5 times, and it continues to accelerate and expand. So take a look at them, talk to them, and it might be interesting for you as well. Third, Lanit, a leading multidisciplinary group of IT companies in Russia and the Commonwealth of Independent States. And it's the largest Russian system integrator and a key partner of more than 280 major global producers of high-tech hardware and software solutions. So let's full cycle of software development for both government and commercial organizations. And it provides development and implementation of high-load information systems for national, regional, municipal levels. Last but not least, the golden sponsor, Flow Health, which is the #1 most downloaded female health app on the planet. And using the power of data science, AI, and various medical experts, the app provides curated cycle and ovulation tracking, health insights, expert tips, and a community of users that answer your questions and get support. The Flow team strives to improve the health and well-being of every woman worldwide. And please make sure that you check their site, check them out as a sponsor. And they are on the Pine platform. And I'm told they have job openings. So go ahead and check them out. Finally, please don't forget to ask questions and give feedback on all the sessions that you attend today. Please also rate the sessions that you attend. because that helps us, me as a speaker, to improve for next sessions. And also do share your experience on social media, on Twitter, on LinkedIn, all of those platforms. And the organization and all of the speakers, including myself, we're looking forward to your questions and to your comments. So thank you for that. And once again, welcome to the DevOps Pro conference. Let's get started with the keynote. So today, my keynote, my talk is going to be about my experience with pushing systems or running systems in production. And my experience is shaped by many, many years as an independent IT consultant, working with a lot of companies over here in the Netherlands, where I'm based, but also worldwide, speaking to lots of people, working on conferences and speaking on conferences. And all those experiences have shaped the story I'm about to tell you, where I will talk about what we can learn in IT from the space program, which is a pretty cool thing. So please do remember to ask questions. I'll check the Q&A at the end of the talk and discuss whatever I can and answer whatever I can. Cool. Let's get going with a little bit of story time. And I wasn't born then yet, but in 1969, specifically July 1969, something interesting and historic happened. And this was the launch of Apollo 11. Apollo 11, as you may well know, was the first manned mission that landed on the moon. Three astronauts, Buzz Aldrin, Neil Armstrong, and Michael Collins, were in a small craft and made their way to the moon and ultimately landed on it. Now, if you look at pictures from those days, for example, this is a picture of Neil Armstrong in the lander, you notice that this is a very cramped situation, right? There's not a lot of room. There's a lot of buttons. It's very flimsy, and there's only a little tiny window to look out of. But hey, they used this thing to go down to the moon, to land on the moon. And so on July 24th, 1969, they actually made it to the moon, right? And this is history, of course. But the thing I want to talk to you about today is that it almost didn't happen. And I have a little video that explains why.
On July 20th, 1969, the first humans landed on the moon, but they almost didn't make it. The Apollo guidance computer was trying to process a few too many computer commands at once during the landing sequence. The exhausted computer, with only 72 kilobytes of memory, sounded its 1202 alarm, signaling an overload. NASA's Jack Garman had a cheat sheet and was confident the computer could be trusted. Margaret Hamilton and the software engineers at Draper, formerly the MIT Instrumentation Lab, had programmed the computer for such a scenario due to a happy accident. During early testing for the Apollo 8 mission, Hamilton's daughter came to work one day and was playing with the simulator. She accidentally triggered a pre-launch sequence while the simulator was running another program, and she crashed the simulator. Hamilton had never expected this error and quickly added additional error prevention software that saved Apollo 11's moon landing. With only seconds of fuel to spare, NASA decided to proceed, and the astronauts were given the go for landing.
Okay, everybody, let's hang tight and look for landing radar.
The rest is history.
And indeed, the rest is history. As we well know, Apollo 11 landed. And then a year later, Apollo 13 launched. And Apollo 13 had a few different problems. Now, this started as a routine landing, or a routine journey, rather, to the moon. And during one of their, again, routine steps, something interesting happened. Something exploded on the side of their spacecraft, which you can see in the picture now, like half of a panel blew out, which was not supposed to happen. It also doomed their moon landing, so they weren't able to land on the moon. But what it triggered was this cascade of creativity, of people coming together to help these folks get home safely, okay? To make sure that their spacecraft was able to support them home and become a lifeboat, essentially. And so this is one of the pictures that, to me, captures the Apollo 13 mission perfectly. This is engineers showcasing a system that they built from components you can find on the spacecraft. And this particular system was a CO2 scrubber. So it removes CO2 from the air, which, as we all know, is a problem for humans to breathe. And they basically used their ingenuity and problem-solving skills to get this problem solved. And then ultimately, these 3 guys landed on the Earth safely. Now, fast forward a few years to 2020, last year. Another historic thing happened. And this time it was not landing on the moon, but it was the first commercial mission to space, the first commercial manned mission to space, I should say. And these 2 astronauts rode atop a Falcon 9 rocket, SpaceX rocket, in their Crew Dragon module, and docked with the International Space Station, which worked out beautifully, right? And the picture is I mean, this thing looks so cool, right? This is almost sci-fi, but it actually happened. So what caught my eye as they came back, landed safely and started their debriefing, they shared a few of the things that they were talking about. So one of the things they were talking about is how their mission was just like the simulations, how there really was nothing that, that went awry, that went wrong. And I think I detected a little bit of boredom in their voices, right? Like nothing ever happened. And that was pretty cool. But something else caught my eye is this statement that SpaceX provided audio recordings of earlier launches and used those audio recordings of the launch and reentry during their simulations, so that the training would be more realistic. Now, all these things, this story about space, I think we can summarize in a few takeaways. So one of the things they did a lot of was testing. Okay, you verify components, you verify systems and software based on specifications and contracts, which is an important thing. Another important thing or takeaway is that these folks did a lot of experimentation, right? Integrating stuff, finding failure modes, happy accidents, intentionally triggering issues to figure out how their systems behave and how they work. And also, they did a shit ton of simulation, right? All sorts of scenarios, throwing the kitchen sink at these astronauts, highly unlikely failures, multiple failures at the same time, all in order to build experience. And then lastly, all these things together combine to adaptation, to be ready for whatever may come. Now, you may say, okay, Michiel, this is rocket science, right? That wouldn't work here because we don't have the budget, we don't have the people, and we certainly don't have the time. And that may all well be true. I mean, space is a very expensive endeavor. But what can we actually learn from this space stuff, right? Well, let me take you into a few things, because ultimately we have to realize that in IT, all of us, most of all of us, are building complex and distributed systems. Let me describe a little bit what I think is a complex and distributed system. Okay, it's a system that is nonlinear, which may appear chaotic, unpredictable, counterintuitive. The change in an output is not proportional to the change in an input. Okay, these systems are typically hard to reason about. They're difficult to describe. System-level behavior is difficult to explain just by looking at the individual components of the system. The system as a whole reacts differently than you would think from just looking at the individual components. And this also leads to the fact that not a single person can fully understand the system, right? It's simply too much. And to try to understand it, we humans, as mere mortals, we construct models in our head to simplify things, essentially. But that also means that the model that we have in our head does not match the reality. So the way we think about our systems typically is not typically does not match the reality of how those systems behave. And we see surprising failure modes in these systems, right? We did not expect certain things to happen. We say stuff like, that's interesting. When these systems fail, typically they fail in a different way than if you, again, were to look at the individual components. So, okay, now that we know that we have complex distributed systems, some people might say to me, okay, how about we just build simple stuff, right? What if we just build simple things? And if we can't do that, we can simply plan better, right? If we know all this stuff, we can plan for it. Or can we just be more careful? We should not make mistakes. Because after all, if we get rid of human error, then these systems will just work fine, right? The thing is, perfect software doesn't exist. David Woods in this YouTube video discusses how no plan survives first contact with a disaster. And the plan in this case is perfect software, and the disaster is production traffic. Perfect software doesn't exist, and software will always behave differently under production loads than you think it does. But the problem with people thinking that human error is everything behind this, and if we simply get rid of human failure, then we're good, is echoed online here and there, and that's this is not a unique. This is this statement I found on LinkedIn the other day. Human failure is the biggest threat to security. Therefore, we periodically train our employees. Sure. If you train your employees, they will not make mistakes anymore. We all know that, right? No. So, okay, but what if we just test more? If we look at our complex distributed system, we just test more, we learn more about our system. And, we may even use the testing pyramid in our software development, right? We have all these unit tests that are cheap and fast to run. And we've gotten rid of most of our end-to-end tests because they are flaky and unstable and difficult and expensive to run, and they take hours. And so, yes, the testing pyramid is a very good starting point and something we can absolutely use to define our mix of testing. But there's one significant problem with testing, and that is testing never shows the absence of bugs. Testing validates what we know and what we have seen. Right? If we have a regression test, that test is there because we've seen a bug. So we know it exists. We know that problem exists. And then we write a test to make sure it doesn't happen again. And if you were to look at this picture, this is the quadrants of knowns and unknowns. Testing is in the upper left corner. So testing validates what we are aware of and what we understand. It doesn't work in any of the other quadrants. Okay, cool. So let's just stop changing then, because if our changes end up building a complex distributed system, if changes cause problems, if changes cause incidents, then we maybe should just stop changes. And again, this is a way of feeling that you see more often. For example, I found this on the internet the other day, and again, this is not unique either. Some person saying that incidents that result from change is a very effective metric to a degree that it's actually not a metric of system failures, but it's more a measure of departmental failures, ergo people. So if we were to just simply get the number of incidents associated with change down, then we're fine. No, we're not, because research has shown that if you don't change, that's going to cost you, because the competitor is going to. And so if you stop changing, you're going to add delay. You're going to add costs of delay. And those opportunity costs, or the losses in opportunity costs, can go into the millions, right? So we cannot stop changes. Crap. So how do we deal with all this stuff? And that's actually the core of this talk, dealing with the unknown. specifically building up your adaptive capacity. In his talk about being poised to adapt, Dr. Richard Cook states 7 steps that you need to take in order to be poised to adapt. So all these steps, 1 through 6, are basically steps we know and we do, right? We think we know what a platform is supposed to do. We think we know how it works, what the behavior means. We can change our system in such a way that the way it works changes or what it means changes. And we think we are able to predict whatever that change does. And we can then force the platform, we can deploy the change so that the platform actually changes. But the interesting part to being poised to adapt is here, being prepared to deal with the consequences. And that's what this session is all about, being prepared to deal with those consequences. Now, a good friend of mine, Steve Smith, he talks about adaptive organizations and how he thinks there are 7 steps or 7 capabilities that an organization needs to have in order to be adaptive. So the first one is you should have an adaptive architecture. And what do we mean with that? Well, things like auto-scaling, circuit breakers, health checks to ensure that system failures are corrected automatically and do not progress further into your architecture, into your system. That if you have more load, that your system scales up and down to deal with it. And that's an important feature of an adaptive organization. Second is incremental deployments. And I'll go into that a little bit in detail in a minute, but think of, small and frequent deployments, blue-green deployments, canary deployments, rolling updates, automated rollbacks, all these things to ensure that we have lots and lots of little deployments in order to reduce risk. Automated provisioning, where we use tools like Terraform, Ansible, Packer, what have you, to automatically create, modify, maintain, delete, update infrastructure, servers, virtual machines, what have you. And then the fourth, ubiquitous telemetry, observability, and operability. 5, chaos engineering, running controlled experiments on your system. 6 is you build it, you run it, or you own it, you run it, right? The DevOps mentality, if you will. And the last one, post-incident reviews, doing blameless postmortems, doing lots of knowledge sharing, doing lots of learning. But today I'll focus on these 4 items: incremental deployments, telemetry, chaos engineering, and incident reviews. So on deployments, what's crucial about deployments? Well, we want to integrate early and we want to integrate often, which means that the work I'm doing, I need to integrate with the work that my team is doing, that the rest of the people I work with are doing. Not by pulling their work to me, no, by pushing my work to them. That's the only way we can integrate. So we don't think of people isolating themselves on branches. No, we work together on a shared code base. So integrate early and integrate often. Why? Well, that helps to make things small. And making things small is essential because inversely, if you make things big, if you take big steps, then if they fail, and the chances of failure are high, they will fail big, right? Big bang releases fail in a big way. Big steps fail in a big way. And the thing is, if you turn that around and you take small steps, you might still fail, but the failure will be lots smaller and lots easier to correct, and it will cost less. Imagine climbing a mountain. You don't take one step to get to the top. You take lots and lots of little steps, and you can course correct on any of those little steps. And let's put that in a picture. So what this picture is showing you is 2 release schedules. The left of the picture, an infrequent schedule. The right of the picture, a frequent schedule. So what you see on the left is we don't do a lot of releases. And as we are building up, as we are working towards our release, what we are doing is building up inventory. We're building up all this code that's sitting on the shelf because we haven't deployed it. So it's not doing anything. It's certainly not adding value at this point. But what it is doing is accumulating risk. The risk that A, it doesn't work, or B, nobody's interested in it. Okay, so as we deploy, what we hope to do is to convert this risk into value. And then we reset and we build up this risk all over again. Now, on the right side of the picture, you see lots and lots of small releases, many small releases. So the thing here is we still build up risk, we still build up inventory, but it's substantially reduced compared to the left side of the picture, right? We have significantly reduced our risk exposure here. So the beauty of deploying functionality in small batches is that you can earn value faster and reduce risks at the same time. And that's pretty cool. Now, research has shown that this is the case, right? And it is often assumed that if we deploy software more frequently, that we must accept lower levels of stability and reliability. And the research actually shows that is not the case. So if you look at a book like Accelerate, which is peer-reviewed research in the science of DevOps, you see that elite performers, high performers, deploy 200 times more than low-performing teams. And what is most interesting is that their time to recover from a failure is very much faster, and their change failure rate is a lot lower. So yes, these folks are doing a lot more deployments, but by doing those many small deployments, they're actually reducing the risk profile while allowing to go to production quite quickly, and a lot more quickly than low-performing teams. So if you then look at, for example, continuous delivery, the book or the Bible, they also say continuous delivery is about delivering value to users safely and quickly in a sustainable way. And none of this is new, really, right? Okay, on to observability and operability then. So in the basic sense, observability is about this. Lots and lots of cool graphs on hallway monitors around your office, or in these COVID times on your screen at home. But wherever they are, however you display them, these graphs, this telemetry, this info gives you an inkling, gives you an idea of how your system is performing. And that's also the definition of observability, right? It's a measure of how well you can infer how a system is doing from looking at the external outputs. And the external output, for example, is what's the render time on my homepage, or what's the response time on my API endpoint. It doesn't tell you directly how your system is doing, but you can infer how your system is doing from those pieces of information. And so observability is about this pyramid. It's the pyramid of reactive and proactive activities on your system. So proactive is monitoring and alerting, right? Looking at these inputs and triggering alerts whenever they exceed some sort of threshold. And then reactive is once you actually see there's a problem, you dive into it. You start your debugger, you use tracing, you use profiling to figure out where your system is slow, where there are errors, where they are coming from, et cetera, et cetera. So observability is this mix of proactive monitoring and reactive debugging and tracing and profiling. And together, this is observability. Now, operability is what is defined as the properties of a system that make it work well in production, which is also called the operator experience, aka how is this system, how easy is this system to use in production, not for your end user, but for you. So if you are woken up at night because your system is throwing errors, how quickly can you figure out what's going on? How easy is it to understand the health of your system at that point? How easy is it to change things in a running system? How easy is it to get data, to get dashboards? All those properties influence the operability of a system. And as you cannot inspect quality into a product, right? The quality is there or isn't by the time you inspect the product. I mean, take a look at a car as it runs off the assembly line. You cannot make a crap car a good car at that point, okay? So either it's crap or it's good, but because it's a finished product, it's very difficult to inspect quality into that product. And inspecting operability into a product is as difficult. It means that as you build stuff into your product, you need to take operability and observability into your mind as you build out that product. Because operability, observability are essential to building up good feedback loops. Now, you may know this picture, which is the plan, code, build, test, release, deploy, operate, and monitor loop, which is the theoretical paradise version of feedback loops, right? In reality, it often turns out to be this. We have lots and lots of build operations going on. We don't deploy very often, but we do lots and lots of building. We deploy once in a while, and we measure some stuff, and the measurements typically don't end up with the people doing the building. So there's a lot of measurements, but those measurements are typically left with the people doing the measuring, which do not have the context of the people doing the building. And the key to working feedback loops is actually having those measurements connect back to the people doing the building. All right, so next part is about expecting failure. And I like failure. Failure teaches us things, right? Failure, I think we should embrace. Failure is not something to be afraid of. Failure is not the opposite of success. In fact, failure is something we need to induce in our system in order to learn. And that's where chaos engineering comes in. So chaos engineering, as defined in the book, basically by Casey and Nora, is facilitating experiments in order to uncover systemic weaknesses. And expanding that definition a little bit, it's experimenting on a distributed system, here it is again, in order to build confidence with that system's capability to withstand issues in production, to withstand turbulent conditions in production. And so chaos engineering in the quadrants is here. It's the two right quadrants of this picture. Things we are aware of but don't understand yet, and things we are neither aware of nor understand. So, for example, I have a very simple system that connects to a database. And I have a feeling that if we were to go to 10 times the load we are seeing now, that the database will have a problem. We just don't know if it actually is at that load increase or the way that the database is going to misbehave. We simply haven't seen it yet. We haven't tried it yet. So we are aware that we will have a problem in that situation, in that scenario, but we don't know the extent of the problem. We don't understand it yet. And there may even be other weaknesses in our system that we simply haven't thought of yet. So chaos engineering helps us color in that part of the picture. And so one of the cool tools, of course, in this space, and a lot of you probably know it, is called the Chaos Monkey. The Chaos Monkey was started by Netflix as a tool to basically turn off virtual machines at random, right? Here's a virtual machine, it dies. There's a virtual machine, it dies. Which is cool because it teaches you about how your system survives infrastructure going away. And infrastructure dying is not a unique thing, right? It happens all the time. It doesn't only happen in cloud situations. Also, bare metal service can die. And the moment we actually are able to deal with that and not get anxiety about it, not freak out about it, that's a good situation to have. Now, chaos engineering is not just about breaking things. And while breaking things is cool, of course, we all like to do that. I know I do. Chaos engineering is not just about breaking things. It's about learning how our environment, how our system deals and reacts to certain conditions. And chaos engineering is also not just about breaking production. because people may simply not be ready for you to break production, right? It may cause too much of a problem. It may cause too much impact. So before you go ahead and start turning off your production environment, maybe just start small. Take small steps in order to build up confidence, and start on your testing environment and learn how your system and your organization reacts to introducing failures, to turning stuff off, to deleting things, to removing things, to switching off network, whatever you can think of. And then as you increase your confidence, as you improve and you learn, then you maybe can progress to your acceptance environment. And finally, you can start doing this in production. Now, the way we learn to do this is by doing something called a game day. Now, the game day was coined as an event, a half day or a full day, where you conduct a single experiment or multiple experiments if you have the time. But typically, you conduct one experiment against your system, a component of your system, in order to validate or invalidate a hypothesis about how your system behaves. And the hypothesis, like I described, may be if we get 10 times the maximum load we've ever seen, our database server will crash. So the game day is about simulating 10 times the load and seeing whether our hypothesis, the database crashes, is actually true, or whether something else happens. And this game day will tell us a lot, teach us a lot about how our system responds and how our system is resilient or not in the face of turbulent conditions. Now, in the last part of this keynote, I want to talk about incidents. Incident response, maybe, well, really about incident analysis. So incident analysis is the activity that occurs when the incident has been resolved, right? We have an incident, things are on fire, we start putting out the fire, and then at some point the incident is deemed closed, it's deemed done. Cool. So now we need to analyze what happened. And what I want to tell you is about incidents. Don't freak out if you have an incident. Incidents are a fact of life. Incidents are a measure of success. If you don't have any customers, you probably won't have any incidents. Surely you will not have any incidents with customer impact. So having incidents is a measure of success. It's a measure of having impact. And while incidents can be very annoying and can be very detrimental to your health, they are a fact of life. And how you respond to them, that is your choice. And let's let you into a little secret. Incident analysis is actually not about the incident that just occurred. Because there's so much more to learn from an incident than just looking at the incident. So please also stop using the words root cause analysis. Why? Well, root cause analysis, there are two things connected in two things in that phrase that are problematic: root and cause. Root implies that you don't have to look any further because it's the end of your analysis, right? You can't go further than the root. The tree starts at the root. And cause, singular, implies that there's only one cause, that there actually is a cause, that there's causality. And please go ahead and read this book if you have the time, Understanding Human Error by Sidney Dekker. What you call root cause is simply the place where you stop looking any further. And that's unfortunate. So if you do your analysis, simply call it incident analysis. Don't call it root causes analysis or root cause analysis, because that implies that you do not understand causality, or that incidents usually have a serious chain of events and factors that all contribute to that single incident. What is incident analysis about? It's about establishing a learning culture, a culture where we can share information transparently, and we can talk about that, and we learn about how our system is doing under adverse conditions. we learn not only about our system, but we learn about ourselves as well, how we are doing in such a situation. And one of the key parts of a good incident analysis is the blameless postmortem. And recently, people have started saying, okay, maybe it's not about being blameless, but about being blame aware. Because humans, you, me, all of us, we have a tendency, a natural tendency to point the finger at people, to blame others, right? Things happen. Or even more counterproductive, we have a tendency to blame ourselves, right? When an incident happened, when something that you might have caused happened, we say, I should not have done that. I should have known better. I should have looked at this manual before. I should have consulted this and this person before. And the problem with all these counterfactual statements, because none of what you just described happened, it's completely pointless, right? And what it does is actually deflect from the analysis. So if I were to make a mistake and I were to, for example, delete the production database, and I say after deleting the production database, I should have seen it was the production database and not the testing database. We can stop with that, right? I mean, next time, simply make sure that you check that it's actually not the production database before you delete it, and we're good. Whereas the incident analysis can be much more interesting than that. So the blaming others, but also blaming ourselves, let's get that out of the way first, acknowledge it at the start of the incident analysis, and then get rid of it. Be open and honest. Be open about what you did and why you did what you did, or what led you to do what you did. What information did you have at the time? What pressure did you feel? What steps did you take in order to reach a certain outcome? That helps you to paint a picture of the situation as it was when the incident occurred. And be honest about what you did and did not do. Not in order to take idiotic responsibility or to take the blame again, but no, be open and transparent about what transpired, what occurred. Don't, no velvet gloves. No, don't make it pretty. Don't leave out the messy details. No, include them. Be open and honest. And this helps with accountability. Now, an accountability is not being fired because you delete the production database, right? Because again, that does not solve the problem. It only gets rid of a person who, in a certain condition, did a thing which had serious impact, but was probably never their intent, right? They did not come to work that day. I'm going to delete the production database. Accountability is the other side of professional autonomy and competence, right? Accountability is to be seen to be good at what you do and accepting the consequences when things do not go well. And that means being open and honest about what you knew and did not know and did not do at the time. And ask lots of questions. Ask what and how questions, preferably over who and why. So focus on the actions and the conditions rather than the people, right? If you ask lots of who questions, we're going to point fingers at people. We ask lots of why questions, we may end up doing the same. Whereas what and how focuses on the actions and the conditions as they existed at the time of the incident. And we collaborate, lots and lots of collaboration on learning, on sharing, on improving ourselves, improving our systems. And the improving ourselves, that's the key part. And that's what I want to leave you with. A few years ago, I saw this great keynote by John Allspaw, who is one of the godfathers in the resilience engineering community. He talks about people being the adaptable element of complex systems, not all the auto scaling and auto healing and all the tools and automation that we built in systems to make them more robust. No, ultimately, it's us, it's you, it's me. We are the last line of defense. We are on the front lines, if you will, when an incident occurs. We are the ones that need to deal with that. We are the ones that need to fix it. We are the ones that need to adapt to different situations, to new situations. So when we're building complex systems, we are the adaptable element. And we need to ensure that we are able to overcome these new situations and adapt whatever is thrown at us. So I want to leave you today with a short summary of what I just talked about. Is you cannot test everything. That's impossible. That simply does not exist. You cannot prepare for everything because we cannot know every situation that may occur. But what we can learn is to be prepared to deal with anything. And I leave you with those words. Contemplate them, have lots of fun today and tomorrow during the conference. Absorb all the knowledge you can, and use that knowledge to be able to deal with new situations and become more adaptable. If you can become more adaptable, then I would say that's mission success for me, and job well done to you. So thank you for listening. I'm able to be reached today on the chat in Pine, but you can also find me on Twitter. My Twitter handle is in the view right now. Send me an email if you like this talk or if you want to ask questions later. And please visit my blog, and we can talk some more. And I'm sharing some stuff on there as well. So with that, let's go to some questions. I'm taking a look at the chat right now. There's one question. What about cost per release? Sometimes it is a significant effort. Yes, I totally agree. And I also think it should not be. A release should not be a significant effort. If you do lots and lots of small releases, many releases per day, they will end up being as routine as going to get a cup of coffee. And that's what you want. Releases should not cause anxiety. They should not be events marked in the calendars. They should not be situations where you take a system or an organization down for an entire weekend, for example. Releases should be fast, painless, and repeatable. And then there should not be a significant cost associated with them. Now, getting to that point, getting to lots and lots of small releases that don't cost anxiety and pain and all those things, of course, that's a journey. That's an investment, but it will pay off, believe me. It will pay off in being more stable, being able to react quickly to market conditions, being sustainable, and being safe, and reducing your risk exposure significantly. And that's what I think a lot of us want. So yeah, go for small releases. Another question, how incident management in the company should change. What's my opinion about that? Well, what I described just now, I think incident management in a lot of companies is about people, is about pointing blame or pointing fingers at people. It's about also looking very constricted, very tunneled, if you will, at a single incident. Our database is not able to respond or is not able to deal with the amount of traffic. Okay, we'll get a bigger database server and we're done. That actually only solves that particular condition and that particular instance of that incident, but there will be other things. And I would like people to see incidents as signals, as information, not as things to fix, but as information about your organization, your people, your system, and use that to learn. So, of course, there may end up being very concrete things you want to fix because you saw them go wrong in an incident, but it's not about the incident. And I hope that all answers your question. Now it's time for me to leave you all in the very capable hands of all the other speakers today. enjoy the conference, have lots of fun, learn lots of things, and maybe we'll see each other today or tomorrow. Thanks again for tuning in, and have a great day.